So this is a video about the laboratory techniques making measurement labs. This will be our first lab. And the point of the lab is to demonstrate what the purpose of significant figures is, and also demonstrate the difference between accuracy and precision. And the way that we'll do that is we're going to measure different volumes of water and see how well we can do that. So before I get into the particulars of the lab, I'm going to talk about how you're going to do calculations. How are you going to look at your precision calculation and your accuracy calculation? So imagine you go in the lab and you measure 4 objects that have different masses. Well, actually, you go in the lab, you measure the same object on a balance, and the balance has error associated with it, and it gives you 4 slightly different measurements. It gives you 9.7, 10.2, 10.0, 10.5, but you are measuring the same object. So this is just the natural variance of this instrument, which is quite large. And so the first data that you want to have is what the mean or average value of your mass of your object. And the way that we get that is we just add together your trials. So it's the sum of your trials divided by how many trials you made. So we measured the object 4 times. We had 4 different values. So it's the sum of those 4 values divided by the fact that it's 4. And that gives me 10.075. So the first question is, out of these values, the 1, the 0, the 0, the 7, the 5, which of them are actually significant figures? Which of them actually reflect data that we measured? So what we have to do is now calculate precision. So what we do is we look at, for each value independently, we look at how it compares to our mean. So we take our mean value and we find the difference from the first trial. And we take the absolute value of that, so our difference will always be a positive value. So here's for the second trial, here's for the third trial, and here's for the fourth trial. So these are the deviations from the average. And then the way that we get our average error, which is a measure of precision, is we take the average of these values. So we add them all together, and we divide by how many values there are. There's 4 of them. And this gives me a value of 0.225. And for these average error calculations, we're always going to round that value to one significant figure. So I get 0.2 grams. I can express that also as a relative error. So the way that I take our error here, our average error, and give it as a relative value is we divide by the average. So we take our 0.2, which is this number right here, and we divide it by our average, which is the 10.075 grams. And I multiply it by 100 to make it a percentage. So this is percent relative average error, and that gives me 2%. Once again, I always round to one significant figure. So what I can do with this value is I can figure out how many of these digits are significant. So the rule is we look at the place of this error. So this error place, there's always going to be one digit, but its place is in the 10th place. That means in our actual value, the last significant figure that I can report is in the 10th place. So this 0 here is the last digit I'm going to keep. And then we use my rounding rules. I'm going to look at the next digit. It's 7. So I'm going to round this 0 up to 10.1. So when I report my error, or my value, I'm going to say that it's 10.1. So that's properly rounded, plus or minus my error, and then I'll also include my relative error. So plus or minus 2%. Now we could have used our significant figures rules to figure this out as well. Our significant figures rules are actually more of an approximation, but you can see that I'm adding these numbers together, and they are all accurate to the 10th place, which means that my final answer should have also been accurate to the 10th place. So that would have told me to round this answer to 10.1. You'll see that won't always work when you do your experiment in the lab. That in that case, it won't work that way. You'll have to use this idea to figure out what's the last infant figure you can report. And then next is accuracy. So accuracy is once again the deviation from the true value or the accepted value. So we calculated 10.1 as our experimental value or our measured value. 10.4 grams is the true value. The National Bureau of Standards is an organization that puts a lot of thought into what is the true value of different measurements. So they in their hands they found 10.4. So 10.4 is probably more correct. And so we look at our deviation from what is probably the more correct answer to ours. Once again, this is an absolute value, so it's always going to be positive. That gives me, this is 0.3 divided by the true value, which is 10.4, and times 100% to make a percentage, that's 3%. In general, we'll use the rule of 5% or less is pretty accurate. We'd like to be better than 5%. Over 5%, we're no longer very accurate. The same rule applies for precision. We would like this number to be 5% or less. If it's less than 5%, then we were pretty precise. If it's over 5%, we were not that precise. So now let's talk about the actual lab. And this lab in particular is going to be similar to the other labs that you do as far as formatting the document that you're going to turn in as your lab report. So you're going to have, in your lab notebook, you're going to write this information. You're going to write your name. You're going to write your lab partner's name. So some labs, you'll have one lab partner. In other labs, there'll be a total of 4 people. So you have 3 lab partners. And then title. So the title is something that you come up with, or you can use the title that I used. My title that I used was Laboratory Techniques Making Measurements. You can come up with something else. Measuring volume, precision in measuring volume, accuracy and precision to measure 24 milliliters, anything that you want, a title, but it has to be reflective of the lab that you're doing. And then this little note here says that in some lab notebooks, at the very top of your paper, it'll have a blank spot for name, partner, and title. So you could just fill in right there, or you could write in the actual body of the paper, you could write this information out. Then next, you're going to write an introduction. So you're actually going to write the words introduction. So actually write this out so that I know what portion of the lab this is. And then just write 1 or 2 sentences describing what the point of the lab is. So that's really up to you. Write it as a note. So this is not in the first person. The point of the lab is to blah, blah, blah. So I won't say anything because I want you to write it in your own words. Why do you think we're doing this? And then you're going to write a procedure. And the procedure that you write can be a bullet point. It can be numbered. It can be a flow chart. You can summarize the procedure, which I have down here on the 3rd page. You can summarize this, or you can write it exactly. But you must have the procedure written into your lab notebook. And then finally, you are going to write a table that has all the places that you're going to record your data. So all you're going to be recording are are masses. So you'll have 8 masses to record. And then there will be one other piece of information that I'm going to write on the board for you. This is going to be your true value, so you can do an accuracy calculation. And then, so now you got all your data. You've collected it all. The lab is over. You've cleaned up. And if you have time, you can do this in class. Otherwise, you'll do this at home. But you're going to calculate data just like we did up here. So you can make it exactly look like this as well if you'd like. But I would like you to calculate average mass. I would like to see the work that you did to calculate average mass. I would like you to calculate precision, and I would like to see the work that you did to calculate precision. So I want to see the differences, and I want to see the average difference and where you've rounded it to one significant figure, and I want you to calculate the average error as well. And when you're doing this, I want you to label each section. So in my work, I've labeled that I'm calculating average error here. I've labeled that I'm calculating relative average error. I've calculated that I'm calculating average mass. So don't just have numbers appear on your paper. It should be clear where those numbers are coming from. And then you are going to write your average mass plus or minus the average error plus or minus the relative average error, just like I did at this point. So make sure that the digit in the average error is in the same place as in the last digit of your value. In this example, our digit was in the 10th place, so the last digit we can report would also be the 10th place. And then finally, you're going to record percent accuracy. And then you're going to do that this whole mess all over again, but now for the 50 ml beaker. And then finally, you're going to answer these questions about the experiment. So label this section called conclusion. And when you answer these questions, the thing that I want you to remember is assume the reader cannot see the prompts. So don't just say, don't just answer the questions if I can't see these. So this question is asked, if you needed to measure 24.2 mLs of water, which instrument would be better to use? So don't just write the beaker was better, right? To measure 24.2 milliliters, the best instrument between a beaker and a graduated cylinder is a beaker. The reason why is because the beaker had the least amount of precision and was the most accurate. Hopefully that's not what you find, but I want you to write it in that kind of format. And then finally, the actual procedure itself. The actual procedure is very simple. I'll demonstrate this in the lab, but what you're going to do is you are going to take your graduated cylinder, just make sure that it's dry when you start off. You're going to put it on the balance, make sure the balance is 0, so it should be reading 0 first. Put it on the balance, you'll get a reading, a mass, write down the digits that you see. And remember that when you write down the digits, write down all the digits that you see, so don't round at all. And then taking your water bottle, you're going to try to, as best as you can, deliver 24.2 milliliters inside of the graduated cylinder. There'll be a little bit of error to that, but you should be able to get pretty close to 24.2. And then take your graduated cylinder, put it on the balance, and read the mass. And then record that value. So that is your now, which is called trial 1. So this is your graduated cylinder with water in it. Dump out your water. You don't have to get it dry, just dump it out. And then once again, fill it up to best as you can to 24.2. And then measure it again. That's your trial 2. And then go through that whole procedure one more time. Dump out the water, squirt bottle, fill it up. That is your trial 3. And then do the same thing over again, except now you're going to use a 50 milliliter beaker. When you're using the 50 milliliter beaker, it's almost going to be impossible to figure out where 24.2 is. It's going to be hard to figure out where 24 is, but 24.2 is you're going to be blind to it. But do your best job anyways. The whole point of the lab is to show that you can't really measure out to this kind of precision. So do your best job. Don't try to don't try to invent a method to make it more precise. Just fill up the beaker to where you think it is, take a mass, empty out the beaker, fill the beaker up again, empty out the beaker, do it a third time. So once again, you'll have 4 measurements, the empty and dry beaker, and 3 measurements with water, about 24.2 milliliters of water in your beaker. And then look on the board. At the end of the lab, I will have written this number, and this is your the value that you'll use for your accuracy. This will be your true value, the value on the board. Yep, and that's it.